Hello everybody. I'm Youngman from IBS. In this short talk, I'd like to discuss the role of QCD vacuum in real physical system. And this short presentation is based on the article published in AAPPS Bulletin this year. So what is vacuum? So classically, it is very clear. So vacuum means empty space or nothing. But in quantum physics, a vacuum does not necessarily mean empty or nothing. So the basic reason is that this is the uncertainty principle relation. So in a very short period of time, you can always have fluctuations in energy. And then these fluctuations in energy can create virtual particles. Therefore, in quantum vacuum, you can always have vacuum fluctuations and full of virtual particles, or sometimes you can have vacuum zero energy. So my interest here is to study the role of QCD vacuum in physical systems. So the QCD vacuum is the vacuum state of quantum chromodynamics, and this is the Lagrangian for QCD. So Q denotes quarks, and capital G is for gluons, and small g is for coupling constant among quarks and gluons. And this one is cartoon for atomic nucleus. So atomic nucleus consists of nucleon. Nucleon means a neutron and protons. And neutron and protons are composed of quarks and gluons, and d quarks, u quarks, and gluons. In QCD, why the basic reason why vacuum can be non-trivial is because the coupling constant here alpha s is g squared divided by 4 pi. So this coupling constant becomes very small at very low energy. So if the energy is very high, the coupling constant is less than 1. So you can use perturbation theory, and also the quarks and gluons are interacting weakly. But at very low energy, the coupling constant becomes less than 1, and quarks and gluons interact strongly. So therefore, you can imagine that QCD vacuum can be non-trivial. And it is really, QCD vacuum is non-trivial. There are many candidates of true QCD vacuum structures, such as center vortices, quark antiquark condensate, Copenhagen vacuum, etc., etc. So if the QCD vacuum is trivial, and it looks like this. So positive energy and negative energy only interacts here and nothing. But because of strongly interacting nature of QCD at low energies, you can have quark-antiquark pair in the ground state of QCD. So this is one example of the non-trivial structure of QCD vacuum. And this quark and antiquark condensate is supposed to break chiral symmetry of QCD. So what I want to study is the role of QCD vacuum on nuclear mass and also on asymmetric dense matter. Today, later on, I will mostly focus on this nuclear mass. So what is the issue here? So the mass of the quarks are about 5, while the mass of nucleon is about 1,000. Since the nucleon is composed of 3 quarks, it's like 5 plus 5 plus 5 is 1,000. It's very strange. And in fact, you can do some exercise here. So the thing is that, again, is it true? I mean, 5 plus 5 plus 5 is 1,000? Of course, it's not. So we need to have some other contributions to nuclear mass other than mass of a quark. So this is the issue about the origin of the nuclear mass. And I spin asymmetric dense matter. is also interesting physical system. And here, dense means this much density. And this one, 5 times 1,000 kilogram per cubic meter is the average density of Earth. So therefore, you can imagine how dense it is. It's way dense compared to the average density of the Earth. So you can have such high density matter in the sky, such as in neutron stars. On the Earth, you can create such high density matter through heavy-ion collisions. So worldwide, nowadays, there are many facilities which can create such high density matter through heavy-ion collisions. One of them is round, which will be built in Korea soon. So my interest is here. This is the gluons in the vacuum. So my goal is to understand the role of such QCD vacuum in dense matter. And also, I want to make a simple model in which we can understand quantum matter and nuclear matter on the same footing. So now back to the nuclear mass. So again, simply adding up 3 quantum mass doesn't give nuclear mass. So therefore, there should be some other sources for nuclear mass. So one popular scenario is this from linear sigma model. Here, sigma 0 denotes the quark and antiquark condensate. So if you have quark and antiquark condensate, which break chiral symmetry, you can have nuclear mass in addition to the quark masses. Another scenario is coming from Perry-Tabular model. Here, N plus is for nucleon, N minus is for its paired partner. So here, even though you don't have quark-antiquark pair, meaning sigma 0 is 0, you still have N0. So therefore, in this Perry-Tabular model picture, the nuclear mass is coming from chiral symmetry breaking and also something which has nothing to do with chiral symmetry breaking. So we call it chiral symmetry mass, N0. Now, can you understand such kind of problem starting from QCD? I mean, starting from quark and gluons. Here, these are all baryons, hadrons. I mean, this is nucleon, this is mesons. So if you wanted to start understand this hadrons and nuclei dense matter in terms of QCD, I mean, the simplest way or the best promising method so far is lattice QCD simulations. But I want to construct a model to understand these hadrons and dense matter without using such heavy numerical computations in terms of quarks and gluons. So the thing I want to suggest here is that you can use chiral quantum model or chiral constant quantum model with gluon fields. And these gluon fields will introduce QCD vacuum. And then if you calculate something within this setup, you can understand the role of QCD vacuum in real world and the hadrons and dense matter. So what is the candidate that we are going to use? So for the moment, we are going to use the vacuum called Copenhagen or spaghetti vacuum. So in this Copenhagen or spaghetti vacuum, so you have constant chromomagnetic field in the QCD vacuum, and the expectation value of that constant chromomagnetic field is 0 every year in the vacuum. This way, in fact, you can restore rotational symmetry. So to introduce this Copenhagen vacuum to study things in constant quantum model, to study the nuclear mass, we solve Dirac equation of constant quarks in the Copenhagen vacuum. So since in the in the Copenhagen vacuum, the constant chromatic field can have arbitrary direction. So we introduce this three coordinates for that. And then we solve the Dirac equation in this background. And then we expected that this energy level will be quantized and then and depends on zeta and phi. But interestingly, the energy level is independent of the angles. And here gamma is for spin. Now, since we are working with constant model picture, so in our case, the mass of nucleon is sum of three ground state energy of quarks. So this way we calculate the barium masses, and that are listed here. So first we can find the relation between barium mass or nuclear mass with the H, which characterize the QCD vacuum. So this way we can connect QCD vacuum property to physical observables such as the barium masses. And here, our results satisfies the Gelman-Oku mass relation for barium active. That is also interesting. So in this short talk, I'd like to try to suggest a way to connect QCD vacuum with physical quantities such as nuclear mass. And as a first of applications, we calculate the barium octet masses in the Copenhagen vacuum. And we found that there are some relations between QCD vacuum and barium octet masses. In future, we will extend our work to dense matter. And finally, in many cases, the effects of gluons are buried in the coupling constants of effective field theory. But by doing this kind of thing, I think we can extract some information of non-portable gluons out of Lorentz constants. This is it. Thank you for your attention.